Okay, so these are not. This is not my Linksys in the closet.
No, although the Linksys in the closet is doing in its own small way very much what the so-called big iron routers are doing out on the internet. So let's step back a bit and refresh our foundation about how the net works. Listeners who have not been listening for years will not have heard this before. So I beg the indulgence of those who have listened to every podcast for the last 9 years as we start into year number 10. I remember when I first sort of heard the rumors of an internet, or the notion, like sort of science fiction at that point, of a global network. At the time we had modems, and you dialed your phone to connect to the source or CompuServe or something, and yeah,
that was point to point, one to one. You didn't need a router.
Well, exactly, and I remember thinking, how can all the computers be connected together? I mean, how can that? I mean, because back then the notion was you would need wires to go between them all, and what we now know, we now sort of take for granted, is the incredible inspiration of the original designers was this notion of what's called packet switching, where a given computer would not need wires to every other computer, which was clearly impossible, because then you would need, n times n minus 1 number of wires, and that's just not going to happen when n is large. Instead, you were able to reuse one pair of wires, because the data that was going over those wires had addresses. Rather than the wire itself representing who you were connected to, the wire represented being connected to the world. And then the brilliance was that the stream of data that used to just be a continuous connection between two endpoints, the stream was broken up into packets carrying the addresses of the source and the destination. Essentially the addresses of those two endpoints were the endpoints were not physical as at each end of wires. They were logical as addresses in the packet. So it was an abstraction, a brilliant abstraction that made this work. So then you have individual computers that all have their own wires connected to, one way or another, to this thing called a router. And then the routers were connected to each other, and the routers knew who was connected where. And that's the key. So there's several levels of brilliance here. There's the notion of the abstraction of a connection is no longer the actual electricity. The electricity is now the data flow, and the connection is a logical connection rather than a physical connection, and not rather than an electrical connection. It's a logical connection represented by addresses carried by packets of data. But to make this work, then, to bridge the logical to physical, something needs to know where an address is. We have the notion of addresses, IP addresses, we're all very glib about, IPv4 giving us 32 bits of addresses, but we still need to know where, because the job then, when one user puts one of these packets of data on their wire and sends it to their router, the one they're connected to. The router is like spokes hooked up to a bunch of other routers. And those routers have spokes hooked up to a bunch of other routers ad infinitum. But somewhere, some number of hops, as it's called, a hop is each of these links is a hop. Some number of hops away is the destination. And when the packet of data arrives at the router looks at the address, the destination. There's a source address and a destination IP. Just using the destination IP, it sort of needs to look around at the links it has to other routers and decide which one to send the packet out that is sort of taking it in the direction of its destination. And if that happens enough times, finally it gets to the router that the guy that you're sending it to, the other end is connected to, and then it goes to them. So routing tables is the way this is done. Now, the originators of this system, again, with shocking foresight. I mean, for this thing to have survived basically unchanged. We've tweaked it here and there, but it's pretty much the way it's been. It's just incredible that it's gone from, a research academic platform to this. To an amazing global thing, still basically the same. I'm just in awe of that. I'm sure that when they did 32-bit addresses, when they said how much addressing space should we need, they were laughing at 32 bits. Oh, we're never, come on. Are you sure you want to waste all those bytes on address space? Because we're never going to use up all of that space. Probably port numbers were the same way. Don't you think, how many ports do we really need? Of course, we have 64K ports because we have 2 bytes, and we have 4.3 billion IP addresses because we have 4 bytes, 32 bits. So again, they designed for the future, even though they didn't know what the future was going to be. Which, that's the mark of an engineer. They made some simple divisions of this space. Again, in understanding the challenge of routing, and this is why this is important. They said, let's define different kind of lumps. We'll have Class A networks that will be 16 million IPs. And now, that they were laughing. Again, that meant essentially 16 million is 24 bits. So what that would mean is if you think about 24 is 3 bytes, 3 times 8, that would mean that the first byte would be the identity of the whole Class A network. That is, all networks beginning with 1, and then anything in the other 3 bytes would be the 1 Class A network. And then if the first byte was a 2, that would be the 2 Class A network. And historically, there have been, probably still are. I think HP is like 14. They still, because HP was in there very early, they're the 14 network. They've got all of the IPs beginning with 14. Nobody else has an IP beginning with 14, and HP has all of them beginning with 14. A Class A network. But since you only have a byte, that means there are some limits too, because 0 is reserved and 255 is reserved sort of at the endpoints. So 253 out of the 254 out of the 256 possible. And there are some other ones, like 127 is famously also reserved. And 10, for example, the 10 network, we all know, is that whole Class A block is a private network. In fact, my IPs are all 10 dot here. Because it was just easy when I set things up. So what that means is that there is no public IP beginning with 10. That's all that whole block has been reserved for use inside private networks. It's a so-called non-routable Class A network. But the point is there are very few of those. Only so many combinations of that first byte. So again, these guys said, okay, well, we'll have some Class A networks, but we also want some Class B networks. That is, not everybody needs 16 million IPs. A lot of people who are smaller could get by with 64K IPs. That is 2 bytes worth of IPs rather than 3 bytes. So that's a Class B network where you have the first 2 bytes is the network number, and then the second 2 bytes, the lower 2 bytes, the right-hand 2 bytes, is which IP within that network. So now rather than having like everything in 14 network is HP, now you have things like the 24 Class A, the first byte is 24, and then the second byte is which one of the 24 sub networks is you're talking about as a Class B, and so you have many of the first bytes and then all of the values in the second byte creating Class B networks. And then they went one step further and they said, and for really small networks, let's divide the Class B networks into Class C networks, where a single Class B could be 255 Class Cs, meaning that the first 3 bytes are the network number, and then the last byte is 1 to 254 is the machine within that network. So a Class C network can have 254 different machines in it. So they set these scales. Well, now here's what's brilliant about that from a routing standpoint. The routers on the internet, out on the net, what is necessary for them is to have a destination for every single IP address. That is, if any packet with any of those potentially 4.3 billion IPs arrives at a router, the router has to know where to send it. It's got to have a destination network. And if HP had all 14, had its Class A network all beginning with 14, then because of this hierarchy, because of the concept of networks containing networks, any packet that arrived at a router where the first byte was 14, the router didn't even have to look at the other bytes. It said, 14 is HP. Send it to HP. And back then, HP was a much smaller than it is today, located somewhere on the peninsula in Northern California, and the bytes all went in that direction. So my point is that this notion of networks of networks and machines within a network, that dramatically simplified the job of the routing tables. The routing tables, imagine if there wasn't that kind of aggregation, every router I mean, if it was just completely randomly assigned, every router would have to have 4.3 billion entries. Well, it couldn't, but it would have to, because every single IP would then be looked up to find out where it should go. And so that gives you a sense for the power of this notion of a network. The network bytes at the high end of the addressing space, and then the specific machines at the low end. Because of this division, routing tables could be vastly smaller and much simpler. Now, what began to happen as the internet became popular is it became the case that companies that the organizations, Aaron and the various internet registries, started realizing that they needed to more closely match the IP allocations given to companies to the company's size. That is, here was the problem. If you were bigger than a Class C network of 254 machines, well, then they'd have to give you a Class B. But that was 64,000 machines. And so the problem, there was no other easy granularity. So it would be possible to give someone 2 Class Cs. But what they ended up with was something called CIDR, C-I-D-R, which is classless interdomain routing. Essentially, what happened I think it was in 97, in the mid-90s, was this A, B, and C distinction was broken, was deliberately dissolved, so that instead of there being only byte-size boundaries, the routing architecture was enhanced so that the boundary between what is the network number and the machine number could then fall anywhere within the 32-bit space, meaning that this was classless. There were no more A, B, and C. It was, well, they're limited to powers of 2, so that you would go from, for example, 256 with in what was used to be a Class C, you could slide the boundary 1 bit over to the left and get 512, or 1 bit again and get 1024, or 1 bit again, and so forth, to double the size of your network rather than going to 256 times the size of the network. Well, as all of this happened, routing tables grew. The architecture of routing pretty much held together. That is, an ISP would have a block of IPs, and it would have lots of customers within its address space using those IPs, and it would have entries in every router out on the internet for its network, so that every router on the internet, when an IP came in that matched the network number of this large ISP, that router would know which interface, which connection to send that packet to. And so that packet would bounce from router to router until it got to that ISP's network. Well, the allocation of IP addresses is done through something known as anonymous systems, AS numbers, ASNs, anonymous system numbers, and every entity on the internet that is given a block of IPs receives an anonymous system number. Those used to be 16 bits long, but that's another thing that we outgrew. so that for some number of years now, they've been 32 bits long, because we outgrew the total number of entities that wanted a block of IPs. I remember when I was first getting serious about networking, Mark Thompson of Analog X fame suggested that I register for an AS, that I get an anonymous system designation. And what that would have meant was I would have received a block of 256 IPs from Aaron, and they would be Gibson Research's IPs. And what's significant is that they would never change. That is, I could carry those with me wherever I went. It never seemed like that was something that I needed. I never pursued that. But as a consequence, I don't own my IPs. When I was with Verio, I had a block of IPs with Verio. I was briefly with XO. I changed IPs to when I was within XO's umbrella, essentially borrowing from their IP space. And now I'm with Level 3 with a chunk of IPs that Level 3 has. So I've always been using the IPs of the ISP I'm in, but many larger organizations don't. They did what I could have done, and that is applied for IP space and got it. So they are an anonymous system with an allocation of IPs which are portable, meaning that those never change, and as they move, those IPs go with them. So what that means is, and this is part of what has happened over time, which has caused a fragmenting of this otherwise sort of perfect routing. One thing that's happened is that the invention of CIDR, the classless interdomain routing, has allowed allocations in smaller pieces. But as those allocations were given anonymous system designations, and as those anonymous systems moved to other providers, suddenly when a block that was under a given network's umbrella and thereby could be routed with a single routing table entry, when that block moves somewhere else, now it can no longer be routed within that umbrella routing entry that gets the packets into that data center. It needs its own entry in every router on the internet saying, whoops, here's an exception to this otherwise this big block of IPs. Here's an exception to that. And for this smaller block, you got to send it over there. Now, the way the routing tables work, again, it's a brilliant concept, is they perform what's called a longest prefix match. The prefix is those bits on the front from the left end which specify which network the packet goes to. And so the idea is, when you think about it, if a short prefix isn't very specific, that is, there may be many networks that begin with 24, and then it's the next byte which specifies what used to be a Class B network. It's more specific. And if you match all 3 bytes, the first 3 bytes, then you're really more specific. Now you're down to one of 256 machines in what used to be a Class C network. So the longer the match of the prefix, the more specific you get. And so what the routers do is they look at an IP address of a packet coming in, and within their table, they find the longest routing table entry that matches, and that tells them where to send the packet. So what we want in order to minimize the total number of entries in the global routing table is what's called aggregation. That is, we want a large ISP that has within its umbrella many smaller networks. We want that ISP to not to broadcast, or in routing terms, to advertise all of those networks, because it's needless. If all of those little networks, sub-networks within a large ISP are going to the same ISP, don't send or advertise them all separately on the internet. Instead, just have one entry that because they're essentially that encompasses them all, so that the data can get to the ISP, and then the ISP can privately route them where it needs to. So, but the problem is, to the degree that aggregation of smaller networks is not possible, we need individual entries in all the routers on the internet, in so-called the global routing table. And it's, as I said, it's when anonymous systems that own blocks disaggregate from the original block provider that it's then necessary to put an exception, essentially, in the table saying, whoops, sorry, here's a longer prefix match for this particular guy, send it over here. So over time, as we've talked about the whole IPv4 space depletion problem, over time, the number of IPs, as we know, has grown and grown. IPv4 has grown and grown and grown, and is now we're now at a problem where we're running out of IPs. This has created not only IP growth, but in fact, one of the contributors is that for a long time there were Class A size networks unused. When we first talked about Hamachi, they were using the 5-dot network because it was unroutable. It would have never been allocated. Nobody owned any 5-dot IPs. So, and it was very clever for them to use that. But we then decided, whoops, we need to start using these IPs. But the problem was, as we began using, for example, the 5-dot network, we were chopping it up in small pieces. No longer were we going to give huge allocations to people just because no one was ever going to be able to use all these IPs. We knew that was no longer true. So right off the bat, over the last few years, all of the remaining unused space has generally been chopped up into smaller pieces than it was historically. So each of those, and those different pieces went to different people, different anonymous systems, so they all needed their own entries in the global routing tables. So it's been a combination of the way the net evolved, the tendency to allocate more smaller pieces as we began to run out of space, and then just the churn of motion of chunks of space disaggregating so that it couldn't be routed under a single umbrella and brought into a local domain where it could then be routed privately. But essentially what used to be private routing had to be pushed out into the public because of disaggregation. As a consequence of those things, we have been approaching a point where some routers have a problem. There are a class of older Cisco brand routers. They're Catalyst routers. I had the model number I thought here, but I don't see it in my notes. Oh yeah, the 7600 series routers, which are known as the Catalyst 6500s. They have a capacity of 1 million entries, yet the default is set to 512,000. So 512,000. In the notes here, I show today's global routing tables, how many entries there are. Now, not every global router has exactly the same number of entries, because in some cases they've got a lot of local networks which are local to them, so they don't need entries for their routers for their own networks, but other people need entries for those networks. So the actual number of entries varies from router to router, but they're right around 500,000. Generally about 500,000 is where we are. Last Tuesday, something happened which suddenly pushed we've traditionally seen continuous but rather slow growth. Last Tuesday, an event occurred, and something pushed the global number of routing entries over the default setting for that particular older Cisco router, which could only handle 512,000. We're at 500 now normally. We're actually back to 500 now. It was just actually a mistake that was made by Verizon's autonomous systems, their ASNs 701 and 705. They aggregate a large chunk of routes. They have 72.69 and then all of the networks underneath. So that's a class, what used to be a class B size, 72.69. What happened was by mistake, they pushed their sub routes out onto the public internet. They disaggregated what they would normally be routing privately. They pushed them out publicly. 170 additional routes appeared, and that caused the number of routing table entries to go above the number that particular Cisco router could handle, and all just in spotty fashion all over the internet, those particular Cisco routers stopped being able to route. There's something called TCAM, which is it TCAM? Yeah, TCAM. It is a very fast associative memory, a content addressable associative memory technology, which allows these routers to essentially do incredibly fast line speed lookup in order to process these tables. And that is it is settable, but the default is 512. With this mistake that Verizon made for a few hours last week, the router, the entries went to 515. And when that happened, when those tables overflowed, the routers fell back to software lookup, which is vastly slower than hardware-based, virtually instantaneous lookup. And that's essentially what happened.
And Verizon immediately blamed Netflix for the whole thing. No, I'm just kidding.
Yeah. So Verizon realized they made a mistake. It wasn't their intention. It was just a plumbing screw up where they published all these routes publicly that they intended to keep private. And that that ballooned the routing tables. The routers sent all of these new routes out. Many of them, unfortunately, couldn't handle it. And so it created, spotty outages, weird sort of effect throughout the internet where some people couldn't get to places and some people could. And then, as soon as those routes were removed and the network sort of healed itself and went back to being okay. Now, Cisco anticipated this a few months ago. In May, they sent out a notice to everyone who's got these routers they know of saying, hey, the global routing tables are approaching the default limit for these routers. What's interesting is IPv6 entries take 2 slots, whereas IPv4 takes 1 slot. So right now, the routers have a capacity of 1 million entries. About half of them, 512,000, are allocated. There's like a divider which divides that total space into IPv4 and IPv6. So 512 entries of IPv4, and because IPv6 takes twice as many, it takes 2 slots essentially for its larger 128-bit address. Those routers can handle 256,000 IPv6 entries. Right now, the IPv6 table is only about 10,000 entries long. So what the people who have these routers last week realized their routing tables overflowed. All they have to do is just change the configuration, maybe to 768, for example. Since IPv6 is still the global IPv6 table is still so small that threshold can be moved from the half point to the 3/4 point. That'll give plenty of breathing room for IPv4 growth, and really IPv4 can't grow much more. We're hitting the ceiling there, although it could continue to disaggregate, and so there could still be, even when we stop allocating new space, as chunks of IPv4 break apart and need their own table entries, they'll consume additional table space in the global routing table. But it's looking like we've got plenty of time for IPv6, and hopefully we'll have less of a problem with IPv6 since it's got, massively large network space. There shouldn't be nearly the same kind of disaggregation problem nearly as quickly for IPv6. So that's what's going on with the outage that we had last week, and some really cool information, I think, about the global internet routing and how it works.
I'm just glad to know we can blame Verizon for the whole thing.
Makes me happy. There's a silver lining there.
The only way it'd be better if I could blame Comcast. Wow. No, of course they didn't do it on purpose. It's a simple error, and it was going to happen sometime.
Yes, it was as we've been creeping near this. I mean, actually, this is better that it happened this way, that it was like a little balloon that was a mistake that was then able to be fixed. Because if this was the actual organic growth that truly hit 512,000 for the first time, there would have been no fix in an hour.
That's a good point. Yeah.
Yeah,
you need all those.
So this was like,
yeah.
This is a perfect little wake up call for those people who realize, oops, we need to take that note we got from Cisco in May a little more seriously.
Yeah, is it a simple upgrade?
Yeah, it's just a matter of changing a number in a config file.
It's a firmware. Oh, it's not even that.
Yeah, no, it's not even that. It's just the default is 512,000.
So there's enough RAM. It's not that the hardware can't handle it. It's just a config.
Correct. You simply chain. You actually, if you don't have an entry, it divides your memory in half, IPv4 and IPv6. And so all you have to do is add an entry to say, I want it not half and half, but 3/4, 1/4,
right.
And then you're good. You're fine. Really, really interesting.
Yeah, fascinating.